Hello learners, I am Dr. R.B. Malati, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. I welcome you all again to the course Essentials of Surveying Application and Techniques. Today we will discuss remote sensing and GPS, two technologies that work hand in hand and facilitate detailed mapping, monitoring, analysis and playing an important role in environmental management, urban planning, agriculture, disaster response and navigation. Let us first look into remote sensing. Remote sensing means observing and identifying features on the Earth's surface by detecting the electromagnetic radiation that these features emit. This method has become particularly important with the development of satellites, which have revolutionized everything from weather forecasting to space exploration. The use of remote sensing has also greatly enhanced our ability to manage natural resources, monitor land use and protect the environment. Remote sensing, particularly when combined with the ground surveys, has completely transformed how we conduct topographical surveys. What once required extensive manual labor on the ground can now be done more effectively from the air or space. This technology gives us a broad, almost bird's eye view of large areas, allowing us to see things that would otherwise be invisible to the naked eyes. We can observe the Earth in multiple bands of the electromagnetic spectrum, which provides us with a comprehensive view over time. So, the core principle behind remote sensing is based on the behavior of photons, which are tiny packets of electromagnetic energy. Photons exhibit both wave-like and particle-like properties depending on the situation. According to quantum theory, these photons travel through space in discrete packets of energy moving at the same speed and direction defined by wave theory. The energy of these photons is directly related to their frequency, a relationship defined by the equation E is equal to hv, where h is the Planck's constant. When it comes to remote sensing of the Earth's surface, we use reflected energy in the visible spectrum and emitted energy in the thermal, infrared and microwave region. By analyzing this reflected and emitted energy, we can generate images that reveal variations in the Earth's surface. This process of capturing data across different wavelengths is known as multispectral remote sensing. The resulting images may show variation in gray tones in black and white images or difference in hue, saturation and intensity in color images, all of which help us better understand the materials and features we are observing. So, if we look into the history of this Indian remote sensing IRS, India has a long and proud tradition in space science dating all the way back to the Vedic period. During those ancient times, Indian scholars made detailed observation of the sun, moon, planets and stars. They even had a calendar that accurately predicted the movement of planets and eclipses. One of the famous astronomers of India named Brahmanda was born in 476 AD and made significant contribution to the study of space. Fast forward to the 17th century and you will find Raja Soy Jai Singh, who took Indian astronomy to the next level. He built observation in 5 cities, Jaipur, Delhi, Mathura, Ujjain and Varanasi, to make detailed astronomical observation. These observations were used to study the skies and gather important data about the stars and the planets. India's modern journey into space began in 1963 when a two-stage sounding rocket was launched from the small village called Thumba, located on the west coast of Kerala, close to the equator. This was a starting point for the India's space exploration effort. In the 1970s, India started demonstrating its capabilities in the space applications with experiments like the satellite instructional television experiment and the satellite telecommunication experiment. These experiments were carried out with the help of satellites from other countries. Around the same time, India built its own satellites such as Aryabhatta, Bhaskara, Apple and the Rohini series. Additionally, India developed experimental satellite launch vehicles SLV-3 and ASLV. A major milestone was achieved in 1983 with the successful development of INSAT, a series of multi-purpose geostationary satellites. But the real birth of Indian remote sensing happened in 1988. That year marked the launch of the Polar Satellite Launch Vehicle PSLV, which was capable of launching a payload of 1250 kg into a polar orbit about 820 km above the Earth. Even though humans had been trying to map the Earth's surface for a long time, whether from treetops, mountains, or even high altitude balloons, the ability to view the Earth in its entirety only became possible with satellites. Over the last few decades, space-borne remote sensing capabilities have grown tremendously. Today, satellites have become the primary source of information about Earth's resources and environment. India's journey in remote sensing is evolving from ancient astronomical observation to cutting-edge satellite technology. Today, India boasts one of the largest and most advanced fleets of remote sensing satellites, making significant strides in space-based observations. Key satellites like the Cartosat series provide high-resolution images important for urban planning and disaster management, while the OceanSat series monitors ocean resources and weather patterns. The RISAT series uses radar imaging to keep an eye on agriculture and forestry even through the clouds, and the RESOSAT satellites help manage land and water resources across the country. With satellites like GISAT-1 offering near real-time images and HISIS capturing detailed data across various wavelengths, India continues to push the boundaries of remote sensing can achieve. These advancements not only enhance our understanding of the Earth, but also play an important role in managing natural resources and responding to disaster, solidifying India's position as a leader in space technology. So, we are speaking more on images. So, let us see how satellite images are created now. Satellite images are created by sensor onboard satellites and transmitted to Earth as electronic signals. These signals are processed by computers to create detailed images of the Earth's surface. To identify objects or features from satellite images, remote sensing relies on specific characteristics called signatures. When we talk about the Earth's surface, we can divide these features into a few key signatures such as vegetation, soil, rocks and minerals, water bodies, snow and man-made features. These features can be studied using different parts of the electromagnetic spectrum, which is basically the range of light and radiation. We generally focus on three main regions: reflective optical infrared region, which ranges from 0.4 micrometer to 3 micrometer, thermal infrared region, which ranges from 8 micrometer to 14 micrometer, then microwave region, which ranges from 1 centimeter to 30 centimeter. Let us see how these features interact with these different regions of the spectrum. So, starting with the reflective optical infrared region. In this region, the sun is the main source of energy. So, let us first talk about how this energy interacts with the various features on the Earth. We know plants are essential for life on Earth. They help to regulate CO2 levels through photosynthesis and balance solar radiation in the atmosphere, which influences weather and climate. Because of this, monitoring vegetation is one of the most important uses of remote sensing technology. From space, vegetation isn't just a single leaf. It's a combination of leaves, stems, branches, flowers, buds, and even the soil beneath them. The way sunlight scatters and reflects off this mix of components makes the reflected energy quite complex. But we know leaves are the main contributors to this reflected energy because they cover most of the plant. So now the question is, how leaves reflect light? Leaves come in all shapes and sizes with different surface textures and internal structures. So their reflectance, that is how they reflect light, can vary widely. Plants effectively absorb energy in the ultraviolet and visible parts of the spectrum for photosynthesis, but they don't absorb much in the near infrared region. Beyond 2.5 micrometer, plants absorb more energy, but sunlight is weaker in these longer wavelengths. Most of the energy reflected by the plants comes from the surroundings. So, in the visible spectrum, that is a light we can see that ranges from 0.4 micrometer to 0.7 micrometer. The absorption by leaf pigments dominates how leaf reflects light. Specifically, blue, which is around 0.45 micrometer, and the red, which is around 0.67 micrometer regions, these are absorbed by chlorophyll, the pigment responsible for photosynthesis. And green region, which is around 0.55 micrometer, the leaves reflects this light, which is why they appear green to us. Again, leaves with low chlorophyll content reflect light differently and appear less vibrant. Next, we have near infrared region, which is in the range of 0.7 micrometer to 1.3 micrometer. In this region, the internal structure of the leaf plays a big role. About 40 to 50% of the light in this region is reflected, with very little being absorbed. The leaf's mesophyll structure, that is the inner tissue, is a key player in this reflection. Different plants have different internal leaf structure, so this reflectance in this region varies more than in the visible spectrum. Lastly, we have short wave infrared region, which is in the range of 1.3 micrometer to 2.7 micrometer. In this region, water content in the leaf is a major factor. There are three strong water absorption bands, 1.4, 1.9 and 2.7 micrometer, that affect how much solar energy the leaves absorbs. The more water in the leaf, the less it reflects. The leaf is dry, it reflects more light in this region. Now, the reflectance you see from the whole part or tree as captured by a remote sensor isn't just from the leaves. It is a mix of reflection from the leaves, stems, branches, soil and even the shadows. This overall reflection is called the canopy reflectance. And in the near infrared region, that is a multiple layer of leaves have the most significant impact here. And in visible region, the impact is minimal, and in the short wave infrared region, the impact is moderate. So, when a sensor captures the reflectance from the vegetative cover, it is actually capturing a mix of reflection from the vegetation and the soil underneath and the shadow. This mix is especially important in areas with low vegetation cover where the soil's reflectance plays a big role. For example, in agriculture, where crops planted in rows initially reflect light mostly from the bare soil. But as the plants grow and cover the soil, the reflectance is more from the vegetation. The sun's angle, the sensor's viewpoint and other factors like leaf transmittance and arrangement also affect what the sensor picks up. And to analyze vegetation accurately, we use a measurement called the Normalized Difference Vegetation Index, shortly called NDVI. So, this NDVI is given by reflectance in the infrared regions minus reflectance in the red region by reflectance in the infrared region plus reflectance in the red region. This NDVI values ranges from -1 to 1, and they tell us how healthy the vegetation is based on how it reflects light in these regions. When we are looking at NDVI or any other remote sensing data, we examine how different parts of this electromagnetic spectrum interact with various plant variables. For that, concept of electromagnetic waves should be understood. The electromagnetic spectrum extends from gamma rays to radio waves. These waves are produced by the motion of electric charges. The visible spectrum, called light waves, occupies only a small portion of the electromagnetic spectrum with wavelengths between 0.40 micrometer to 0.70 micrometer. Here, what are the light rays? Yes, you know already. They are the visible spectrum which excites our vision, and within the spectrum, violet light has a shortest wavelength and the highest frequency, and red light has the longest wavelength and the lowest frequency. So, now the next question is how electromagnetic waves work. When a charged particle oscillates, it creates changing electric field. These electric fields induce changing magnetic fields around them, and this interaction continues to propagate the wave through space. When the magnetic and electric waves propagate in a homogeneous and isotropic media, the direction of the two fields are at right angles to each other, and both the fields are at right angle to the direction of propagation. And this electromagnetic waves are characterized by frequency, wavelength, intensity, direction of travel, and the plane of polarization. The distance between successive crests of the wave is called wavelength. It is usually represented by lambda and is measured in meters. The height of the crest above the mean position of the wave is called amplitude. Having understood wavelength, amplitude, now let us see the relationship between the wavelength, frequency and velocity of electromagnetic wave. Let lambda be the wavelength and nu be the frequency and c be the velocity. Then c is equal to nu into lambda, which is equal to frequency into wavelength. And the wave number k is equal to 2 pi by lambda. And the period of the wave denoted by t is equal to 1 by nu. And the angular frequency omega is equal to 2 pi nu. So, now let us move to the topic polarization. As already discussed, the electromagnetic wave is made of electric and magnetic fields, both being mutually orthogonal and transverse in the direction of propagation. If the electromagnetic wave is considered to move in the z direction, its electric vector lies in the xy plane. Now, if the direction of the electric field is random and does not follow any particular pattern, we call that wave unpolarized or randomly polarized. But if the electric field is in a definite direction, we see a linearly polarized wave, which is often called a polarized plane. And when the electric vector lies in the plane of incident, it is called vertical polarization. When the electric vector is at right angle to the plane of incidence, it is called the horizontal polarization. And the plane containing the incident ray and normal to the reflecting surface at the point of incidence is called the plane of incidence. Here, the waves, which has a constant phase relationship both in time and space, are coherent with each other. For a complete coherent radiation, the beam of wave should have a single frequency and radiation monochromatic and direction of motion of wave parallel. This coherence may be of the following types. First is a temporal coherence. This type of coherence takes place only if the phase difference is maintained even after traveling a distance. Monochromatic waves generally experience the temporal coherence. Next, we have spatial coherence. This type of coherence takes place only in pure plane waves, that is the parallel beams. The surface defined by the locus of the point that have the same phase in an isotropic medium is called a wavefront. The isotropic medium is a medium in which speed of the wave is same along any direction. I hope you know this already. So, with this background, let us see the role of electromagnetic radiation in remote sensing. The sun is the most important source of electromagnetic radiation used in remote sensing. The sun's radiation covers ultraviolet, visible, infrared and radio frequency region. Maximum radiation from the sun occurs around 0.55 micrometer, which lies in visible region of the optical spectrum. Solar radiation before reaching the surface of the earth gets modified by the atmospheric effects. All bodies at temperatures above absolute 0 degree emit electromagnetic radiation at different wavelengths as per the following Planck's law. That is, m lambda is equal to 2 pi hc square by lambda power 5 into Ex Ch by lambda kt minus 1, where m lambda is a spectral radiant existence, h is a Planck's constant, c is the velocity of the light and k is a Boltzmann constant and T is the absolute temperature in Kelvin and lambda is a wavelength in micron in Kelvin. Reminding again, the sun being the primary source of the electromagnetic radiation for remote sensing plays an important role in our ability to accurately capture and analyze ground features from space. To achieve this, it is essential that sensor should be correctly positioned in space by a suitable arrangement to gather the necessary data across the full spectrum of radiation emitted by the sun. Such an arrangement, which could be a simple typhoid or a complex spacecraft, is called a platform. Initially, balloons and rockets were used to carry the platforms of the remote sensor. But in the present days, due to technological development, aircrafts and satellites are being used to provide suitable platform for the remote sensor. In 60s, aircrafts were traditionally used as the necessary ground data is easily collected over a specified area with a short time period. The major drawback of aerial photograph is it is very high cost, and repetitive photograph of the same area has to be taken, ensuring a sufficient foreaft and lateral overlaps. Space-bound remote sensing satellites have proved an ideal choice for repetitive global coverage as they can move along different paths or orbits around the Earth. The path which is followed by a satellite in the space is called its orbit. So, let us continue discussing the basic principles behind satellite motion and the characteristics of different satellite orbits in the upcoming slide. Satellites are the moving objects around gravitational force of a central mass much as our Earth. Satellites' motion obeys the Kepler's law. There are three laws. Let us see one by one. Kepler's first law, it states that the path followed by each planet in an ellipse with the sun at one of the foci. Now, in case of Earth satellite, Earth is at one of the foci of the elliptical orbit of the satellite. The nearest point of the Earth on the satellite orbit is called perigee, whereas the farthest point is called apogee. The straight line joining the apogee and perigee is called the line of sides. The sides of the satellite orbit is decided by the distance between the apogee and perigee, which is twice the semi-major axis of the ellipse. And when the two foci coincide, the elliptical orbit becomes the special case of the circular orbit. The deviation of the elliptical orbit from the circular orbit is given by a term eccentricity E. Now moving to the next law, Kepler's second law. It states that the line joining the planet of the Sun sweeps out equal areas in equal time. It means the sweeping of the area by the planet or satellite depends upon its distance from the Sun. As a planet or satellite at the perigee is at the least distance from the Sun, it has to move fast so that the area swept in equal time is equal to the area swept when it is at the apogee, the farthest point. The same analogy is true in this case of satellite and the Earth. Few noteworthy points here are, as the time of travel of the satellite is the same, the area swept at perigee is equal to that at apogee, and the velocity of the satellite is more at perigee as compared to that of apogee. Okay. Now, let us look into the next law, that is Kepler's third law. It states that the square of the period of the planet is proportional to the cube of the semi-major axis. It means the period of the satellite or planet is the time taken by the satellite or planet for going around the Earth or Sun once, and is given by t square is directly proportional to a cube, where t is the period of the satellite, a is the semi-major axis of the elliptical orbit of the satellite. It must be clearly understood that Kepler's law described how planets move in the space, whereas Newton's law of motion described why the planets move in the space. The condition necessary for a body to orbit around the Earth is that Earth's gravitational force is equal to the centrifugal force of the orbiting body. We know that Earth's gravitational force is given by gmm by r square, and centrifugal force of the orbiting body square is equal to mv squared by r, where g is the universal gravitational constant, m is the mass of the Earth and small m is the mass of the satellite, and r is the distance of the body from the Earth. And comparing these two equations, we get mr square is equal to mv squared by r, which gives gm is equal to rv square. For locating a satellite orbit and also to locate the position of the satellite on its orbit, the Keplerian elements are generally used by inertial coordinate system. Here is how this coordinate system is set up. The x-axis has to align with the Earth's axis of rotation, and the x-axis should also point towards the Sun at the moment of the vernal equinox, which is when the Sun crosses the equatorial plane from the southern to the northern hemisphere. And third, the y-axis has to be set perpendicular to the x-axis to create a right-handed coordinated system. And also, the few terms should also be known for locating the satellite orbit. First is the celestial sphere. This is a sphere centered on the inertial coordinate system. Second, the inclination of the orbit theta, that is the angle between the satellite orbital plane and the Earth's equatorial plane, defined as the inclination of the orbit. The orbital inclination of the satellite may vary from 0 degree to 180 degree. The satellite's orbital plane and the Earth's equatorial plane coincide, the satellite rotates the same direction as the Earth. If the satellite rotates in the opposite direction to the Earth's rotation, its inclination would be 180 degree, and if the inclination is less than 90 degree, its orbit is called prograde orbit. When the satellite's inclination is between 90 degree and 180 degree, its orbit is called retrograde orbit. Next, we should know right assertion of ascending node, that is RAAN, denoted by omega. It is a point where the satellite crosses the Earth's equator from the southern hemisphere to the northern hemisphere, which is called the ascending node. The point where the satellite crosses the Earth's equator from northern to the southern hemisphere is called the ascending node, and the line joining the two nodes, that is the ascending node and the descending node, is called the line of nodes. The right assertion of ascending node is the angle between the x-axis, and it is measured in the anticlockwise direction from the x-axis. And the value of RAAN is a number which may lie between 0 degree and 360 degree. Next, we should know argument of perigee, ARGP, the angle between the line of nodes and the major axis of the satellite orbit, measured along the orbital plane from the ascending node to the perigee. This is called the argument of perigee. It also lies between 0 degree and 360 degree. When the perigee and ascending node coincide, the augment of perigee is 0 degree. With the help of these definitions, the elimination, right assertion of descending node and argument of perigee, the satellite's orbit may be defined in inertial spats. But to decide the shape and size of the satellite's orbit, we should also know the eccentricity E and the semi-major axis A. So, the eccentricity E defines the shape of the orbit and semi-major axis defines the size of the orbit. Thank you for your attention, and I hope this session has deepened your understanding of remote sensing and GPS and its application. Happy learning!